Okay, let's start. Thanks for attending this webinar. Today, Michael will talk about his experiences running some scientific software into Singularity containers. The floor is yours, Michael.
Okay. Thanks for the introduction, Juan. So the title, The State of Containers, is accidentally grandiose. I was just trying to make it snappy, so I added an extra clause underneath. So by the state, I mean how useful containers are in minimizing the overhead associated with making results reproducible. So for those, hello? For those of you that are unfamiliar with containers and Singularity, which is the software I've been using to build and run containers, I'll just go through a few introductory slides about those things. And then I'll talk about something called a container factory. And so the issue that comes with running containers is that you need root access to build containers on the machine that you build them. And so that rules out building containers on a HPC resource, because you simply wouldn't be able to manage such a platform if so many people have root access. So I'll talk about that. So some of that, the services that I'll mention are specific to the University of Edinburgh, but I think there'll probably be equivalent resources at other universities. And then I'll just be a short section in section 3, just one slide, just showing you how to run Singularity container over multiple compute nodes on the platform. I'm aware there may be some audio issues. Is there anyone who's not hearing anything? Okay, thanks, Juan. So I'll carry on, but if anyone is out there who can't hear, just send a message, and either Claire will. Okay, I think Claire's confirming that she can now hear. Yeah, so the third section, just very short, just showing you what you need to do, the command you need to run a container over multiple nodes using OpenMPI. Then I'll go through some bare metal performance comparisons. And by bare metal, I mean when you just run the code directly on the compute node and comparing that with running within a container. And then I'll finish off with the summary and conclusions and so on. So a container can just be thought of as a lightweight virtualization, much lighter than compared to a virtual machine. The container is less separate from the host, and the container shares the kernel of the host operating system. Really, you can think of as the container as a combination of a Linux namespace and control groups, namespaces, control groups. So namespaces control what a process can see. C groups control what a process can use. So the container OS, the operating system inside the container, must be compatible with the host OS kernel, and this means that the container OS must be based on Linux if you're in a HPC environment, and so Ubuntu would be fine for that. So there was recently Imperial University ran a containers course online, and there were a few people from EPCC who contributed. And this is just illustration, is just showing the difference between a virtual machine and containers. And you can see on the left, each virtual machine has its own separate guest operating system. And the virtual machine software needs to provide a hypervisor, which basically presents to each of the guest OS a virtual hardware layer. Whereas for containers, the appearance and management of the underlying hardware is handled by the host OS. So something else to also consider is that because there's less separation between containers and the host OS, it's more easy to combine the two file systems. So on the left, you have the file system or the hierarchy tree for the host, And when you run your container, you can easily specify a particular folder or path on the host, such that that appears under a different name within the container file system. And that's very convenient, because typically containers are immutable. You can't change them. So having a folder within your home directory, say, on the host that is then mapped to the container file system, that provides a way to run a containerized application with different sets of input data. So that's rather useful, because for some codes, the input data can be very large. And so this flexibility keeps container image sizes to a reasonable level. Now, I said typically immutable because you can take a container image and instantiate the container from that, but you can instead change that into what's known as a writable sandbox. And then you can make changes inside that sandbox, and then you can write that back as a new image. But that's easy to do if you have root access, which you typically won't have on a HPC machine. So I'm just saying at the bottom of this slide that there are various directories that are mounted automatically when you run a Singularity container. So there are other container software programs out there. So why you use Singularity and not Docker, which is probably the most famous one? Well, in Singularity, images are handled as a single file. So the image, the file would be like a gigabyte, say, is what Singularity uses to instantiate or create a container at runtime. And those are handled as individual files called Singularity image files, CIF files. Whereas in Docker, it can be a bit more complicated because you have a number of layers that you need to combine in order to make the container. And also within Singularity, you can run entirely within a user space, so you don't require administrative level privileges to run. And so inside a Docker container, the user has escalated privileges, which unfortunately would make them root on the host system. And importantly, Singularity can support natively, that means at runtime, various high performance interconnects such as InfiniBand and Intel OmniPath. So in short, Singularity is designed for parallel execution. So it's the sort of container software you need if you're intending to run a parallel code over multiple compute nodes. It also has support for the OpenMPI library. So where am I? So I mentioned briefly that you need root permissions to build containers. And so you also need root when you install the Singularity software, unless you specify this option without -set buid. And that basically that means that the container execution will take place within a user namespace. So that allows a normal user to act as root, but only inside the container. That's the situation on the Cirrus machine that's managed by EPCC. But unfortunately, that has the side effect that all containers have to be run within sandbox directories. And this takes a lot of time to set up. If you say we're running over a fully packed node, so on Cirrus that's 36 cores, then you'd have 36 sandboxes that need to be created and stored somewhere on the file system. So that can take up a lot of disk space, and it's really too slow to actually use. So it's better to install with root access. The other time you need root is the time situation that will concern you is when you have to build containers. And so you would typically be forced to build a container on your own local machine where you have root. And this is required because when you provision the container, when you download and install the various packages that make up the operating system, the Linux distributions have put together those packages under the assumption that they will be installed by someone who has root access. And that's the reason why you need root to build containers. So at EPCC, it's as we manage HPC machines, and we will be trying to support users who have containers who will be using them. We really kind of need a better way of being able to build containers ourselves rather than building them on our own individual laptops. And so I explored this idea of having a container factory, somewhere where you have root access. There are naturally always challenges when you're compiling code on one machine but then running them on another. So the code will be typically less performant because you're not allowed to build to a particular hardware. And also there may be issues with compiler licensing and so on. It may be that the compiler is only available on the actual runtime platform. So just jumped ahead there. So I'll talk about how Singularity integrates with MPI. So ideally, you need you'd have a version of OpenMPI, say, that is identical to the OpenMPI running on the host, or at the very least, you can have an MPI library that runs on the host and the container that share what's known as ABI compatibility. And this ABI compatibility, which I guess stands for binary interface, or the last part, is an initiative set up by various MPICH providers, such as Cray and Intel, where they will what they will do is basically ensure that an application compiled with, say, Cray MPT or just standard MPICH will then run under a Cray MPT library on the host, on the HPC host. So Singularity actually has two solutions for integrating the container. So they're known as hybrid and bind. I'll just go through the hybrid method. So this is basically when the MPI installation that's in your container has to link back to the MPI installation on the host. This is especially required if you want to run a containerized code over multiple compute nodes. It's a fairly long command that you need to put together. So this MPI run command is typically one that you would have in your submission script. So there are various parts to it. So you've got on the is the actual parallel job launcher MPI run, which is OpenMPI's parallel job launcher. So that will run and will launch Singularity, which will then launch will instantiate the container from the image file. That's the path to the CIF. And then within the container, Singularity will launch the MPI application. So on this command, you just notice I've got some color coding. The red is a path that maps to the host file system, and blue is the path that maps to somewhere within the container file system. So what you have then when you launch the Singularity job via MPI run is that you end up with a set of nested runtime environments. So MPI run will launch something called a management daemon, open runtime environment daemon. I think that acronym is peculiar to OpenMPI, but in any case, there's some kind of management daemon which will then launch Singularity, and then it's Singularity that instantiates the container and the namespace environment, controlling what the container can see on the host, and then also launches the MPI application. And the MPI application will then load the MPI libraries that are inside the container. And those libraries will then use a programming messaging interface to link back to the MPI management daemon that's running on the host. So for this to work, the container MPI must be compatible with the host MPI. At least ABI compatibility, and if your container MPI, if performance is critical, then you need to find a way of making sure that the container MPI has been configured for the host hardware. So just for completeness, I talk about the bind model. That's kind of a simpler setup, because here you don't use any MPI libraries within the container. So instead, what happens is the MPI application within the container, when it's launched, will then be linked directly back to the MPI libraries running on the host. So this is quite a nice way if you're interested in, if you have to have runtime performance. So if your MPI library is particularly tightly bound to the hardware on the host, this might be an approach you would need to take. Forthcoming examples I'm going to use, I will show, are based on the hybrid model, just so you know. So now I'll talk about the container factory and what I need to do in order to create the containers or build the containers in the first place. So at Edinburgh, we have something called the Eleanor Research Cloud Service, which is based on OpenStack. And there a user can automatically just create a cloud instance, and that gives you root access to you can create an Eleanor account, and within that account you can have root access to any cloud instance. And importantly, once you have set up an instance, and maybe you've provisioned an OS so that it can be a container factory, you can then easily share that. You can make that public, or you can share it with specific users. So from our perspective, we'll be able to share amongst ourselves within EPCC. So we basically have a central location where we can pull all the scripts that we need to build the sort of containers that users of Archer and Cirrus are using. So fortunately, we do have the ability to access a free tier level of resource, which allowed me to test out using a research cloud instance as a container factory. There's a bit of extra information which won't be of interest to you if you're not at the University of Edinburgh. That's just an extra step. You need to set up a storage manager account to get on there to set up an Eleanor project. But once you've done that, we can actually manage our Eleanor cloud instances through a web-based interface called Horizon. And that's what we've, this is what the screenshot is showing here. So to do that, I've got something that's based on an instance based on Ubuntu version 18, and I have two IP addresses, one internal and one external. And obviously use the external IP address, and then I can SSH into my cloud factory from my local MacBook. And I also need to specify the cryptographic key that allows me to do this securely. But how do I actually get into a position where I can access my cloud factory instance from my local command line? Well, I need to set up a public-private key pair to begin with, and then I need to download some Eleanor user credentials, and then I just need to set up a Miniconda 3 environment and store certain packages that support accessing an OpenStack cloud instance. That's quite straightforward to do. Then I need to source my Eleanor user credentials, which I do here, and then I run the OpenStack command to create a particular instance, and that's based on a Ubuntu YAML file, which I'll just show on the next screen. So it's quite straightforward. I'm just specifying here the operating system that the factory instance will be based on, and everything else is fairly vanilla. I specify the name of my key, which I'll be using to control access to this particular instance. And then having done that, I can then go to my the Horizon interface to get the external IP address, and then I can access the factory. And the first thing I will do is set up and install various versions of Singularity. I basically want to have those versions of Singularity that are running on the HPC machines that I need to support. And then I can then use this factory to begin building a container. And I have an example down below just to show the sort of how the command looks like. So in this example, I'm building a container to contain an astrophysical code called Ramses. That runs simulations of galaxy formation. And it's going to run within a container that will then have Ubuntu 19 installed, as well as OpenMPI 4. And the whole thing is specified via a definition file, this .def file. The build takes about 30 minutes, and the resulting CIF file is about 600 megabytes. What's a nice feature is that because the definition file will remain at the factory, and the image file will then be uploaded from the factory to various HPC platforms. When you're on the HPC platform, you can then take an image file and reconstruct the definition script that was used to build it using the Singularity inspect command, which is a useful feature to have. So now I'll just show you what a definition file looks like. I'll show you at quite a high level, so I'm just hiding a lot of detail within the definition file. So this is the one I use to build the Ramses container. So at the top, you've got the version of the OS used in the container. So that when the Singularity builds a container, it knows which OS image to get to begin the construction. And then in the file section, these are various files that need to be moved from the factory, from the file system of the factory into the file system for the container. So that's this /opt that I'm using. And then within the post section, these are the various steps, the various bash scripts that I run to actually provision the container and install various components and to install the Ramses code itself. There are actually many containers, there are actually many sections within a container definition file. And on the right, in this insert box, it's a list of all the possible sections you can have. So you have ones like environment, which is where you can specify the environment that exists at runtime within the container. You have other sections like run script, where you specify the script that be called if you run the container with the run command. And then you have various other sections such as test and labels and help, which are mainly there so that you can then probe the container when you have it on the HPC machine to find out what the purpose of the container is. Oh, the test section will be something that would specify the scripts that would be run after the container has been built, so as to test that the container was built correctly. But all of these sections are defined in the Scilabs user guides, which you can find at the link above. So I appreciate this is quite a high-level view of the definition. So I'm just going to go into a few of these scripts that are referenced here from the post section of the definition file. The first one I will look at is the one for Ubuntu 19.10. Now, Ubuntu 19 has already been set up, but I now need to update various packages and install new packages also. So there's one such as that I've highlighted, such as Squash FS. So that's the compressed file system for the container. And then there's other ones called libibverbs, which is the InfiniBand. So that allows the OpenMPI libraries to be built with InfiniBand support. And I also have extra packages which I've installed that will allow me to build MPI libraries with Intel OmniPath support also. So that's the Ubuntu script. And then there's the OpenMPI script itself. So that calls other scripts below, but the ones I'm interested in, so the things that need to be done here is I only specify the version of the OpenMPI I'm using, so that's 4.0.2, that passes an argument to the script. From that, I can specify the HTTPS link required to download the software, and then I have the necessary configuration arguments, such as with verbs, which specifies the interface that I'll be using for the interconnect, and also I'm specifying the link for the HWLock support also. So a lot of the components that I'm installing within the container will be following a configure, make install process. So it makes sense to put that within the scripts, or within base scripts such as install, comp, so that all of the components can just call those, can call that particular script. And then I have various other another script, update environment, to update all the environment variables and so on. I'll just show you what the script for Ramses looks like. And again, that just grabs the archive file for the Ramses source code, unpacks it, and just a straightforward build within the container. So that's what happens during the build, and in order to make these scripts as reusable as possible, I've just bound everything up and put it as a GitHub in called a Container Factory. So that just means that it's easy to share with other people in my home institute. Typically, other people won't be using exactly the same factory instances as myself. I will take my factory instance, I will share it as an image, and then I can share it with other people who will be able to access it and set up their own Eleanor accounts. They will then fork and clone the Container Factory Git repo, and they can get the scripts that I've set up, and they can also add their own and later push their new scripts to the upstream repo and so on. So that's, I think it's quite, one of the things I was interested in is being able to set up an environment where not just myself would be able to build containers, but other people within my within EPCC, so that we don't keep reinventing the same scripts to build the same sort of containers. So now just some further thoughts about the Container Factory. For convenience, you would want to be able to upload CIF images or Singularity images directly from the container to various HPC platforms. So, I mean, every user of the factory would need to be able to have their own keys to be able to do that. But that would certainly be more convenient than having to download to your local machine, then upload to a HPC machine, especially for people who are mostly working from home. And so that's the details of the Container Factory out of the way. I will now talk about, so once you've got your container image, you've built it and you've uploaded it to say a HPC host of your choice, how do you then launch it, and how do you launch it over multiple compute nodes? Well, here this snippet is something you would have from a Slurm or a PBS submission script. So within this script, I'm using OpenMPI. So the first thing you'll notice, I'm loading various modules, the OpenMPI module, the version that matches the OpenMPI within the container that I've recently built. Now, obviously, I need to load the Singularity module, and now you'll see the OpenMPI command itself. So I'm running the parallel job launcher, and within that, after that, I specify various MPI run options, some of which you'll be familiar with if you look above. So that those are the ones where you specify the number of cores you are going to be using. You're going to be specifying the hosts or the compute nodes which you run over, and also the bind to or some equivalent placement option. I'm also specifying what I known as MCA options, and MCA is an OpenMPI term, stands for modular component architecture, and that's really just a set of frameworks that OpenMPI organize into what it calls layers. So you'll have an MPI layer, you'll have a hardware platform layer, and you'll have a comms layer too. So within that, you have a framework called byte transfer layer, which basically specifies, or it allows you to control at runtime how you want the comms to behave. And the options that I've set up, I've got a HAT SM, which means that I don't want to use shared memory to handle the communications because I'm communicating across multiple nodes. And then I have BTL open IB allow IB true, which is basically telling the OpenMPI runtime to use InfiniBand on my host MPI. And then in addition to that, I call that OpenMPI, pass it the option, then call Singularity. I then, as within the Singularity options, I need to specify exec-bound and then point it to a folder which contains some InfiniBand libraries. And what that means is that when the container image is launched, that will then have access to those InfiniBand libraries, allowing the communications to happen across multiple compute nodes. And so the last part of this MPI run command is specifying the path with respect to the container file FS within. So that's the Ramses binary, and then there are the various commands arguments that are passed to the binary that will then start the Galaxy simulation. So I'll just show you some now results comparing the bare metal performance on a particular tier 2 HPC machine. And this is the Cirrus machine, which we support at EPCC. And it was a version before the upgrade, so before the OS upgrade and before the introduction of all the GPU nodes. So you can see, unfortunately, for the Ramses code running on Cirrus, the scaling wasn't very good. Each plot point is basically showing the average from 3 runs, and the one on the far left is over a single Cirrus compute node, and then you go 2 compute nodes up to 8 compute nodes. So the plot points are on average, and the horizontal bars are the minimum and maximum runtime. So, I mean, one thing it's showing that the performance, there's no real difference in performance between bare metal and containerized Ramses. It's just not particularly scaling very well on Cirrus. I just show some weak scaling results. I should mention that, of course, I'm using InfiniBand, and that's the interconnect on Cirrus, but I'm not using the FDR interface, the one that has a bit rate quoted on the Cirrus website. So I'm using the verbs interface. If you remember, in the build script for OpenMPI, I specified the verbs option. So again, we've got poor scaling for the weak scaling performance, but at least there's no difference in performance between bare metal and Singularity. I looked for, so what happened then was when Cirrus was upgraded, the Singularity that was installed with without set UID option, which then meant that sandboxes had to be set up on the fly, which made Singularity unusable. So I then had to switch to using a different tier 2 resource. And that one was the CSD3 machine that's hosted at Cambridge. That's part of the Dirac suite of machines. And finally, on that machine, I found that Ramses scaled much better. So both again, I'm building Ramses with GNU compilers, typically version 9 compilers, and using the same version of OpenMPI on the container and on the host. And I'm using the verbs interface again. Now, in fact, there's slightly surprising these results with strong scaling, because they're showing that the Singularity is doing better than bare metal, which seems like that shouldn't be possible. The bare metal results I'd done quite a long time ago, and I'd only recently plotted them a few weeks, and I had to have look into this. Whoops, I've just shot forward. And what I found was there was a difference between the bare metal compilation of Ramses. I'd used an early version of OpenMPI version 3, whereas within the Singularity container, I'd compiled Ramses with OpenMPI. So that the performance improvement is down to the increase or to the update in the OpenMPI version. So if they had been the same version of OpenMPI, again, as with the Cirrus results, the performance would have been indistinguishable. So that's the Ramses on CSD3. I wanted to look at some Archer codes, some codes that are well used on Archer and will be on ARCHER2. So these, moving away from the astrophysical domain, these are biological and chemistry codes, GROMACS and CASTEP and CP2K. So I started with some fairly small test cases, and then I tried out each of these codes, running them on CSD3 in bare metal and within a Singularity container, and to see if there was any performance issues in running it within a container. It was, I think I've just shot right ahead. Just have to go back. Yeah, so it was fairly straightforward to build GROMACS within the container. It just required me to have CMake version 3.14. And then when I did that, I found that as with Ramses, the performance is fairly indistinguishable. So this is the 1400,000 atom test case. So it's a fairly healthy runtime, and it's scaling quite well also. So moving on to CASTEP, that was a little bit harder to compile due to the puniness of my Eleanor cloud instance that I had. If you remember, it was a free tier instance, so I only had 1 gigabyte of RAM. This meant that I couldn't actually compile one of the source files because the OpenMPI compiler was allocating memory to do the compilation. So that was it. It wasn't too hard to find a workaround for that. But as I was sorting out how best to do the workaround, I realized that such a process would be useful for those times when the research code running in the container does need to be built on the host, also that it has access to the host hardware in order to make it to maximize its performance. So I'll just go through the workflow I needed to build CASTEP, so that will be useful for showing you a more complex workflow for the CP2K code. Sorry, I'm just jumped ahead it again. So what I'm showing you on the left within this rectangle is the file system hierarchy within the container. So I've got my various scripts that I've stored within the GitHub repo, and I've got my auxiliary scripts that do the basic, the grunt work, the configure, make, install. I've got my OS script for a particular Ubuntu version. I've got my component script for software that's shared by different research codes, obviously OpenMPI or any MPI library, mpitch, things like the mass kernel library and the fast Fourier transform library also. Within my app folder, I will have the various apps research codes within the container, such as CASTEP, and then within those I would have scripts that specify post-factory customization, and those are broken down per host. So I would have one for CSD3, and then for Cirrus, and then presumably and also for ARCHER2 also. So the script that I would have within the CSD3 folder would do something like this. So I would just this is like the workflow I would need to do. I would this is the workflow I would run through on the CSD3 machine, not the script that's within the container. So I would SSH onto CSD3. I would unpack my CASTEP source code in a folder of my home directory. I would then shell into my Singularity container using the image file, which I've uploaded from the factory previously. Then within my Singularity container, which I'm now running on a logging node on the host, I can then just run that CASTEP script that's installed within the CSD3 folder. And that script will then just run through the actual build, but because I'm running on the logging node, I have a larger amount of RAM. Or if I wanted to, I could run under a serial node if that was more appropriate. And then I can build that CASTEP and have that, and then run that CASTEP executable in the same way that I ran the GROMACS container. And I can just show you the results of that. So for that 270 atom test case, the sapphire surface, again, the results are fairly indistinguishable between the bare metal and the containerized performance. So that's great. Both of these examples are quite fairly straightforward to build within a container. I wanted to now do something that was more challenging, a code where there was significantly more overhead in setting up. So that's CP2K. So CP2K is many third-party libraries which you need before you can build the CP2 executables. And a couple of those libraries actually use auto-tuning to actually tune to the underlying hardware. So you can't really run those on the factory. So again, I needed to have this workflow where I would then have to actually build components from a compute node that runs on the host. So again, I within the container file system, I have those scripts which I supply here within a particular folder. And then on the HPC host, I then run through this workflow where I get the CP2K source code. I then shell into my Singularity container on the logging node, and then I basically copy across the various submission scripts into my home folder. I can then exit the container, and if you remember, when you go into the container, the home directory on your host machine is automatically mounted, so I can copy things from the container into the host home directory. So when you exit from the container, you will still see those submission scripts. So now I can just submit those, and that will then do the build on the compute node and make sure, say for example, the libgrid libraries are built against the right set of on the right hardware platform. So I'll just show you what one of these submission scripts looks like. So the one for libgrid. So in CP2K, what libgrid does is it actually builds a whole list of variants of the integrate and collocate routines. And it builds these, and then it runs these, and it times them. And the variants that produce the fastest time, that produce the correct answer in the fastest time, those are the ones used to build the actual libgrid library that's then linked into the CP2K executable. So that was fairly involved, but it actually built successfully. And then I was able to build, actually, I built the entire containerized CP2K build was done on the host on CSD3. I did it in the logging node, and those components that had to be built on compute, that's where I did those. In actual fact, the ALPA and the libint and libxc and plume libraries I could have built on the container factory. And also, I think I could have built the CP2K executables there, but only once I'd built libxs, mm, and libgrid on the host. So it would have been a bit of a multi-staged process. But sadly, after doing that build, I found that it failed in trying to do the H2O benchmark. So there seemed to be a problem in the containerized version of CP2K to do with memory, and in particular when calling one of the Scala pack routines. So that's something that I'm still investigating. But the exact same build that was done on bare metal and run on the CSD3 compute nodes, that worked fine. So there was some issue there that needed further work. So I was trying to really find a complicated code that would really sort of push containerization to the limit to see if it would still work. And I found a point where it doesn't work. So this is something that's under investigation. So just to summarize, for the codes that I ran, Ramses, Gromax, Castep on Cirrus and on CSD3, I found no significant difference between bare metal and containerized performance. And that agrees with other work that's been done. So in this link from the IEEE paper, I think it's a conference proceedings, the authors there looked at a number of benchmarks rather than research, but they compared bare metal with Singularity and Shifter and came to the same conclusions. For further work, I was very interested in seeing why CP2K didn't work, why the containerized CP2K didn't work on CSD3. I think there may be a difference that may be down to differences with proc meminfo. The various values reported from the container don't match those reported when you're running directly on the compute node. But it'd also be interesting to, once I get that working, to compare the bare metal performance of CP2K, not just with containerized that's partly been built on the host, but also containerized that's been built entirely at the factory, just to understand what the benefit would be if you built something like libgrid on the host. And then I need to repeat my strong scaling runs on Cirrus once the installation of Singularity has been sorted out, and also on ARCHER2 once that comes live, and then to run over higher node counts, and then also to do weak scaling runs. There's also some further work to facilitate access to my container factory, but that will just be for people within EPCC. I've got an extra slide about production costs, which won't interest you if you're not at Edinburgh or not working for EPCC, so I'll just skip that. So conclusions: codes that are trivial to containerize are actually perhaps not worth containerizing because the reproducibility overhead is quite low anyway. And those codes that are difficult to containerize, those are the ones that should be, because it then, it basically hides or encapsulates a sort of compilation details that you don't need to worry about. Once it's solved, and then otherwise, that's the sort of thing that would delay scientific output. So we at EPCC, we will need to identify those codes that are particularly time-consuming to build, because they would then most benefit HPC users if containerized. And we think of what we've seen so far, there isn't going to be a performance penalty in running a containerized version of the software. But then you'd have the advantage that once you've got the container set up, you can run it repeatedly to reduce your own results and extend them, but also to run them on other HPC machines as well, which is a useful thing to be able to do. And just at the end are just some codes that I think will be strong candidates for containerization. Thank you for listening. That's the end of my talk. Happy to take any questions. For HPC in general, I don't know. For Cirrus and ARCHER2, it's just Singularity. That's the container software we're going to go for. There was that paper though, the paper that I referenced, I think on the slide, on a few slides back, the IEEE paper. They looked at 3 container applications: Singularity and Shifter, and something called Charlie containers, or something like that. There were 3. So yeah, so question: have you ever run MPI? Sorry, I'm just seeing a few questions that I missed. I'll start with JB. Have you ever run MPI run with a container accessing multiple nodes? Yes, I have. So those are the results I showed for GROMACS and CASTAP. I was running out over up to 8 nodes, and also for Ramses 2. The problems I had with doing that is making sure that the container OpenMPI could see the InfiniBand libraries. So I mean that's for the systems that I was running on, because Cirrus uses InfiniBand, and I believe for CSD3, even though that uses Intel path, that also supports the verbs interface. So I had to make sure that OpenMPI was built using verbs. James Hall said, you mentioned issues with Singularity on Cirrus. We've been building Nemo Ocean model containers on there. Can you elaborate? Well, the problem I have is the test cases that I run is that I'm trying to do a like-for-like comparison with a bare metal run. So typically I'd run a code that's running fully packed on a compute node. So that's 36 MPI processes on a node. And I've just been trying to do that with also inside a container, but that just won't work, because every Singularity instance each has to run inside its own sandbox. So that basically just means that a whole lot of file space needs to be taken up within the temp folder, and that just takes up too much time to get started. And so that really is unworkable. But that's as far as I've got. But I know that there's a change request for Cirrus that will reinstall Singularity in the way it was done before the upgrade. So we shouldn't have that problem in the near future. Matt Probert asked, what is advantage of containerized CP2K over a system install of CP2K on a HPC system? So that CP2K will be tied to the HPC system, so that will be dependent on the libraries that you already have installed there. So if you have it within a container, then arguably you can just move that to another HPC platform and run it, and then or reproduce the same results that you had before, and then be in a position to be able to extend on the work that was done previously on another machine. So you just need to worry about that the OpenMPI that's within the container is compatible with the OpenMPI on the new host. So that's the advantage there. And also with CP2K, with those things that would need to be performance, that may or may not be an issue. That if it was, then we would have to go through that workflow that I outlined during the talk, and you just have to rebuild libgrid on the new host, but you wouldn't have to rebuild all of the other third-party libraries. Rory asked, thanks, Michael. Have other modern container platforms been considered for HPC? Yeah, I think I answered that at the beginning. So, are there any other questions? I don't think there are. I'm not sure if I'm looking in the right place. So someone might have to jog me.
Yes, I don't see other questions on the chat.
Okay.
So I think if there are no any other questions, so yeah, we can close the session. Thank you so much for attending, and thank you, Michael, for delivering this webinar.
Okay. Thanks,
Bye
Chris.
for now.
Yeah, bye.